Okay, so yesterday the end of the lecture was in some way a list of bad news about height theory in the function field case, but height theory is not so useless in this case in the function field, and I would like to quote, to state some theorem which show that it is interesting to study height theory in the function field case. The first theorem, okay, from now on f will be the function of field of rational function of a curve, and we have theorem, we have xf is a smooth projective variety, and suppose that okay, and L ample line bundle, and then we can do two statements. First statement, I will state it in this way. Consider HL, height associated to L, and A constant, and we consider the set SA is the set of point P in xf of f such that the height of L of P is less or equal than A. So the first statement is suppose that xf do not contain rational curve, and SA is Zariski dense, then xf is isotrivial. This is quite good. So what this statement says, okay, if you can bound the height of rational points in this kind of variety, and either they are Zariski dense, so you are in the case of yesterday, or the set of rational point is not Zariski dense, which means something similar to line conjecture. And this hypothesis is not so bad because, for instance, it contains a billion variety, it contains many hyperbolic variety, all the hyperbolic variety. We will speak about this in the following. And so many interesting cases are contained in this property. And there is a second statement, which is also quite useful, that if xf is a general type, and SA is Zariski dense, then xf is birational to a isotrivial variety. So this also is this is a little bit more difficult to prove than this. This is due to Moriwaki. And this is essentially also to him, but it's quite standard. This also is a quite interesting statement, which shows again that if you want to study the arithmetic of a rational point of variety of general type, height theory is useful, because if you bound the height of all the rational points, then the variety will be birational to something which is isotrivial. So it is exactly what the example I quoted yesterday. You take a trivial variety and then you blow up something which is a little bit generic, a little bit which is not defined over C. I wanted to sketch the proof of this, but I prefer, because this was part of the lecture of yesterday in theory, but I prefer to stay here, and you can see this theorem has to my knowledge, the best version of Northcott's theorem in the function field case. So now we have the tool of height theory, and we would like to use it to study the structure of algebraic or rational point on varieties defined over function field. And so I will make a sort of small review of Campana talk of yesterday, just to introduce the question. So algebraic point on XF. So we start with dimension of XF equal to 1, and I will insist a lot on this case. And the situation is the following. Everything is, as explained by Frederic, is controlled by the genus. So we have three cases. Genus is equal to 0, genus is equal to 1, and genus is bigger than 1. And the situation is the following. Here, XF is always isomorphic to P1. So a lot of a rational point. So this is XF is essentially an elliptic curve. I mean, essentially because it can be that you are not up. No. Just give me a second. And second, so that means that potentially dense rational point. And in this case, we have two other cases. So xf is isotrivial. So potentially dense. Rational points, or xf not isotrivial, and so xf of f1 is finite for every f1 finite extension. And this is, let's say, Mordell. It's not proved by Mordell, but it's Mordell conjecture, I say. So let's come to your question. Over number field, there exist curves of genus 0, xf with xf of f equal to the empty set. Example, x squared plus y squared plus z squared equal to 0 over q. Okay, and this is a conic, and you can prove that every curve of genus 0 is essentially always a conic inside a inside P2. But for function field, you have Sen theorem, which says that every conic on over f as a point is the theorem which says that a ruled surface always have a section. So every curve of genus 0 is P1. By the way, just to remark the fact that this is it is interesting to see that the proof of this theorem use some tools that in theory one can imagine that can be generalized in the function in the number field case, but surely you cannot obtain a Sen theorem over function over number fields because of this example. So there is something to understand why in the function field case you always have a point, and in number field case is a question. In the number field case you can have something which is not P1. So, as explained yesterday by Frederick, this is also a sort of, you divide the curves in 3 classes, essentially 2 classes, where in the first 2 classes you always have points, and in the second class you have not so many points in the non-isotrivial case, and otherwise something is isotrivial. And so you are tempted to say that in dimension 1 the structure of xf of f is controlled by the canonical bundles. No, this is true, and you are tempted to say, perhaps this is what happens in the higher dimensional case. And actually, no. The answer is no. So, the things you do is you introduce a code-area dimension, and the point is that code-area dimension, I have been explained yesterday, which is h naught of x kx to the power n goes as n to the power, how you write it, k. And actually, code-area dimension do not control the structure of xf of f. Just to give some example, you take code-area dimension equal to minus infinity, and you can have, as an example, for instance, x, and suppose that dimension of x is equal to 2, then you can have xf, f is, for instance, c times p1 or p2, where if the genus of c is bigger than 1, this as the rational point as a never Zariski dense, and here the rational point are Zariski dense. So you see that there are two examples of variety with the same code-area dimension where the behavior of rational point is completely different. And then just to say is code-area dimension is equal to 0. The situation is a little bit more stable. You conjecture that xf, that rational point are potentially dense. And there are a lot of cases where it's known for a billion surfaces, for many K3 surfaces, for enriched surfaces. There are many cases where things is known. Code-area dimension equal to 1, same problem. Then code-area dimension equal to minus infinity. So there are cases where the rational points are not potentially dense, and there are cases where rational points are potentially dense. So if you just use code-area dimension, you will not understand the structure of rational point. This is why, for instance, the deepest point of view of Campana may be in light what's going on. And then you arrive to code-area dimension equal to 2. I'm thinking to surfaces. And the main conjecture is xf non-isotrivial implies that xf of f is never Zariski dense. No, this is false. This is false. Non-birational to isotrivial surface. As I said before, you can find something which is non-isotrivial, but it is birational to something isotrivial. So you see how you have to be careful about statement in the function field case. Because, okay, here you say nothing. But here is, if it is isotrivial, then you have a lot of rational points, so it is potentially dense. And then you say, if it's not isotrivial, you suppose that anyway you have a lot of rational points. So in both cases, you suppose that after extension, you always have many rational points. So isotriviality doesn't seem to play a role. But of course, the difficult case is when it's not isotrivial. The point is when you want to say that there are not many rational points. That is difficult because isotriviality makes things complicated. And so the nice thing is that the aim of this school is about Vojta conjecture, and Vojta conjecture I will state a version of Vojta conjecture which in some way do not care about rationality or about the presence of rational points. It just is about height, inequality of heights. So then you can interpret this inequality of heights using, for instance, Northcote's theorem. So I will speak now about a version of Vojta conjecture. So I need to introduce some notation. Xf is smooth projected. And then if I take F1, an extension of F, it corresponds to a curve B1 with a morphing, with a covering of B. And I will denote by D. And if I have a point P of Xf of F1, I will denote by D of P, something which is related only to that. This, by definition, will be 2 genus of B1 minus 2 divided by the degree of alpha. And this is called the discriminant. And discriminant because using Hurwitz's formula, you can easily say that more or less this measures the ramification of this morphism. Because this is, okay, exercise. Okay. And now I will state the Vojta conjecture. Is yeah, it's independent of P, but if I write, It's just a matter of notation, because in the following I will always write d of p, but if there I wrote d of b, then you would say to me, would ask to me, what is d of p? Because, yeah, that I want to say is we will always speak about discriminant of a point. So this is why I want to speak about a point. But you are right. So the Vojta conjecture says, I will say it in the more general version, more difficult version, is you consider epsilon bigger than 0 and d a number, then there should exist a closed set such that for every p, for every f1 over f, such that f1 f is less or equal than d, and every p in xf of f1 minus z epsilon d, we have that the height with respect to kx f of p is less or equal than 1 plus epsilon d of p, see, plus O epsilon d of 1. Okay. You see, I make no reference to isotriviality of x. I make no reference to the structure of x. Just say this is a conjecture. And what is important, yes, and it is important to remark that in many cases, suppose that you take xf of general type, which is not birational to something isotrivial, this will imply that the rational points are not Zariski dense, and etc., etc. So I would like to make some remark on this conjecture. First remark is there exists this hypothesis in the conjecture, but in the case where we can prove the Vojta conjecture, these hypotheses do not play any role. So Vojta said that he wants this hypothesis. It's safer, but we don't understand exactly the meaning of this hypothesis. Second thing is this coefficient here is very, very ambitious. You can have a weaker version simply by saying you do not choose epsilon, but I will say weak Vojta conjecture is replace 1 plus epsilon by there exists a constant A such that kxp is less or equal than A d of p plus O of 1. This is also very interesting as a conjecture and is a priori less ambitious than this one. So you don't know how small this constant may be. A particular thing is this constant may depend on x, and this constant do not, for instance. And exercise, state a version of Vojta conjecture in the logarithmic case, so where you have a couple x and a divisor d, which is a simple normal crossing. You replace everything by second part is study the case when x d is p1 and 0 plus 1 plus infinity, this divisor, and deduce ABC conjecture for function field. So what I want to say is you state this in an open version, so where you have a border. You say this, so you just have to put here the logarithmic canonical shift, so kx plus d, and here you have to change this by intersection with the border. So I just write what is this. This is h kx d of p less or equal than 1 plus epsilon d of p plus n1 d of p plus O of 1. This is intersection counted without multiplicity. And then you apply to this situation, and you will find the ABC conjecture, the usual ABC conjecture, and you can prove it. It's an exercise. So this shows that, a priori you can state the same identical conjecture in the function in the number field case, but even the simplest case of the number field case at the moment, up to what is written on the web, is out of reach. Okay, up to what Mochizuki says. Okay, I want to say that even in isotrivial case, it is not known. And it is interesting even in the isotrivial case. And I would like to say when it is known case. First case is when omega 1 of xf is ample. And we will come back to this. But it is the weak version. This is Moriwaki. Second case is omega 1 xf big and xf isotrivial. And this is the famous theorem of Bogomolov. Okay, let me say just to show why this is the second theorem, is in the isotrivial case, the Vojta conjecture, the weak Vojta conjecture, is the following. X0 variety defined over C, let's say of general type, there exists a closed set Z inside X0, which is not everything, such that for every curve B and morphism alpha from B to X0, such that alpha of B is not contained in Z, we have a degree of alpha up a star of kx less or equal than a constant times 2g of B plus 2 minus 2 plus another constant. This is the isotrivial case of the Vojta conjecture. And so now people who know the Bogomolov theorem see that this is the case. Why this is the isotrivial? Because you can just suppose that xf is x0, so, and then you apply this. Third case, which is known, is if xf is hyperbolic and isotrivial. I will, hyperbolic means okay, I will not explain. Hyperbolic means that there exists no map f from C to X. Every map from C to X, analytic map from C to X, is constant. And another case which is no, I can write it here. And here is also a weak version. Another case which is known is if dimension of xf is equal to 1. And here is the strong version. And this is a theorem by McQuillan and Moriwaki and Yamanoi. And I want to say strong version means with 1 plus epsilon. And I also want to say is that D plays no role. And D plays no role also here. The D which is here. So you can forget this part. So this is why I am a little bit, I don't know how to understand this thing. And more or less up to recently, there is a preprint by McQuillan which proves with if dimension of xf is equal to 2 and c1 square is bigger than 2 times c2, and you obtain a weak version. but this is just well, is announced. I believe it, but I didn't verify all the details. And as far as I know, this is yes. I forgot. There exists, if xf is a general surface in a general complete intersection surface in a abelian variety, we have also a weak version, and this is brought back. And the difficult case is when the surface is a divisor in a abelian variety of dimension 3. And up to this, I don't know any other case known. And yes, I would like to speak a little bit about this case now, just because it's very nice to see how the power of function field enters in this situation, and where you can do something which is not possible to do in the number field case. So let's see the study the case when omega 1 of x is ample. So you have xf and like this, and I look to omega 1 of xf, and suppose that this is ample. What this means? It means that I can look to p omega 1 of x, which is the projective bundle associated to this vector bundle. And over this, we have a tautological bundle, the O of 1 of each fiber, and to say that this is ample means that L is ample. This is equivalent to C. And what is okay, let's study, since we are in lack of time, the isotrivial case. So what is very important is that you have x naught, you have p of omega 1 of x naught, you have your tautological bundle, and you suppose that you have a curve alpha from B1 to here. So since you have this map, you also have a map from alpha up star of omega 1 of xf, or of x naught, to omega 1 of B1. the image is a line bundle inside B1. So by functoriality, you get a derivative map. So this map can be lifted like this. And because of this, you see that alpha prime alpha star of L is a subline bundle of omega 1 of B1, which implies that the degree of alpha prime alpha star of L is less or equal than, divided by nothing, is less or equal than 2 genus of B1 minus 2. And this feature exists only over function field. Over number field, the main problem is that you do not have this lifting, and you do not have the possibility to find a line bundle whose intersection with your point, so whose height, is related with the discriminant of your point. This exists over function field. Over number field do not exist at the moment, at least. So this is a very important thing. And the situation is that now L is ample. So call this map P. So there exists a N such that L to the power N minus P upper star of Kx is ample. That means that the degree of alpha prime upper star of L to the power N minus P upper star of Kx is surely positive. And this, you use this property, and this implies that n times 2g of B1 minus 2 is strictly big than the degree of alpha prime composite by pi. This diagram is commutative, so this is alpha upper star of Kx, which is exactly the weak version, the version of Vojta conjecture in the isotrivial case, because this is independent on the point. So you just bound the degree with respect to the genus. And after, I will speak about the non-isotrivial case, and then we will speak about something else. Okay.